thanks for everyone to be here today. And so today I'm going to talk about quantum effect again. So last week we had Yentao giving us a talk on Bell inequalities, and it's very, very much related to what I'm going to tell you today. There's going to be some overlap, but hopefully not too much. So there's still interesting things to hear today. Also, I'm not 100% an expert on that, but I've been discussing quantum mechanics here a lot at iTHEMS with different iTHEM members, and part of Christy. And so thanks to everyone for this nice discussion. And also, I wrote the abstract yesterday before starting to write on the board, so I was full of ambitions. But after I started to write on the board, I had to streamline the talk a bit. So not everything that is in the abstract might be on this board. Sorry about that. Okay, so basically, even if you don't know what quantum physics is and you have no idea what a quantum effect is, you might have some feelings toward it, thinking that it's something bizarre. You might have heard things like the Schrödinger cat being dead and alive at the same time, or neither dead nor alive. So you might have an idea that whatever a quantum effect is, it's probably something very, very peculiar that goes against your intuition. But at the same time, what I want to discuss today is a more down-to-earth approach, which is how do you write a quantum model? And you'll see that when you write a quantum model, it gives you some very well-defined predictions. And this is why you can do quantum mechanics on a daily basis without getting crazy, because this gives you some prediction for the system. It's going to give you actually, and this is one of the takeaways of this talk, it gives you a statistical prediction for the possible outcomes and the frequency in an experiment. And it does so in a very well-defined way. But it does not tell you anything about what's happening in a single run of the experiment. That it will not tell you. It will not predict that. Yet, and that's another takeaway, and this related very much to what Yentao showed last time, this is not like a classical stochastic model. There's a difference. And there's a difference at the level of prediction. There are certain things that can be predicted by a quantum model and not by a classical probabilistic model. And I'll get to that. And one of these things is precisely that you can validate certain inequalities, the Bell inequalities, with a quantum model, and you cannot do that with any classical probabilistic model with some caveats. And that's what I would call a genuine quantum effect. That's my take on what is a quantum effect. Some things that you can predict with a quantum model that you cannot predict with any classical model. Hence, for me, this gives me a practical way to prove that a system is quantum. If you can find some prediction that a system will have with a quantum model and not with a classical model, and you observe this quantum prediction to be valid, you can show that your system is quantum. It's kind of operational take on what is valid. Okay, but to describe that, let me first show you how you write a quantum model for a system. And I'm going to take as an example a spin one-off. So it's not the easiest system, but it's one that is often used for this discussion. So what is a spin? You can think of a spin as a magnetic moment attached to a particle. Okay, this is something that is going to couple to a magnetic field, and it's a vector in a three-dimensional space. I call it S, and it's coupled like a magnetic moment to a magnetic. Okay, so it's carried by a particle. Let's say that very simple. The fact that it's a spin one-off is encoded here in the fact that its norm is going to be h bar over 2. Okay, so how do you describe the state of this? Well, in general, we want to break down our systems in subparts that we are going to model mathematically. And in this case, and we will call that the degrees of freedom. We will run down the equations of these degrees of freedom, general, be it for a classical or a quantum model. And in this case, well, the spin is a vector in 3D space, so you can completely define it by looking at its projection in a basis. Okay? So here I'm going to call this projection on the basis x, y, z, sx, sy, and sc. And these are going to be the degrees of freedom for my system. X, y, sx, sy, s. Okay, now if you want a classical simple model of the system, how are you going to represent these degrees of freedom? You're going to represent them with numbers. You're going to give numbers to the degrees of freedom. Say sx is something, sy is something, sz is something. For example, here you can take that it's 0, h bar 0, which would simply mean that your spin is in the y direction. Okay, this would correspond to the representation in the classical model of the spin being in the y direction. What does it predict? Well, it predicts that if you observe your spin, you'll find it pointing in the right direction, in the y direction. Okay, and this will predict it in a single run. In a single run, if your model predict that, you should find the spin aligned along the y direction. Okay, but you can imagine also that you don't have such a precise knowledge of your system. and you have some ignorance about the state of your system. And so you can describe it now using a probability distribution, stochastic model. In which case, for example, you can take the distribution of the spin being given by a Gaussian like this, and you can see that in this so I've taken this Gaussian here, and you can extract not what's going to happen in a single run. This model does not tell you what you will see in a single run, but it will tell you statistically what you will see if you repeat the same experiment many, many times. And you can extract, for example, the expectation value of where the spin is going to point in every direction. You can extract the average value of the projection of the spin along the y direction. And it's pretty easy to see that in this case, sorry, that was a mistake here. Should be this one. Yeah. So if you look at this probability distribution, you can see pretty obviously that it's centered at h bar over 2 for sy. So on average, you'll measure the spin to be in the direction sy, and the components on x and z are going to be 0. But it's not always the case, and there is a certain variance that you can also compute. But you can extract all this information from the probability distribution, not what you see in a single row. Okay, so this is all pretty standard. Now, how do you do a quantum model? So for now, I think everyone is familiar completely with this, and now this is going to be the part where people are probably less familiar. So a quantum model is much more obscure and abstract in its formalism at first. So first, how do we represent our degrees of freedom? Here it was with numbers, here it was with numbers weighted by a probability distribution. In a quantum model, the degrees of freedom are represented by operators, Hermitian operators acting on any of the space. So it's a certain mathematical value. Okay. And in addition, the state of the system that, if you want, is the analog of the probability distribution in this case, is going to be a vector psi in this Hilbert space. And the Hilbert space is, let's say, a complex vector space. So at this stage, it's quite abstract. But for spin 1/2, this is actually pretty simple. For spin 1/2, this complex vector space H is 2-dimensional. And so you can represent, for example, your state by any 2-dimensional complex vector that is normalized to 1. So here, for example, this vector that I call arrow up 1 is an acceptable state for the system. It's 1 over square root of 2, component 1, component out. And this is normalized to 1 according to the norm in Hilbert. So that's an acceptable state. And you can show that you can represent your spin operators with these 2x2 matrices that I've written here that are proportional to the Pauli matrices. Okay, so this is the formalism, but now it's not telling you how you extract prediction. So you need additional postulates for that. Or from this number, can I extract what I'm going to measure for the spin projection? So there we go here. What quantum mechanics is telling you is that first, in any experiment that you make, the possible outcome that you can measure for an operator is going to be one of the eigenvalue of the operator. So if your quantity O is modeled by an operator O, the only thing that you can see in an experiment would be the eigenvalue of the operator. So in this case, for example, for your spins, if you want to measure the spin along the Sx direction, for example, you look at your operator, you find its eigenvalues, and it's going to tell you what value you can measure. And in this case, you will find that the only value that you can measure are going to be plus or minus h bar over 2. Meaning that when you look at the direction of your spin in the experiment, you'll find its projection along the x-axis either being plus h bar over 2 or minus h bar over 2. It's discrete. It's not continuous. It's already a bit of a feature, a quantum feature in a sense, okay? And actually, this is true for any of the spin projection. Okay, first prediction of the model, extracted from this formalism. The second prediction that the quantum model is going to make is, as I said, the frequencies and the statistics. So you can compute what is going to be, on average, the value of a quantity with this formalism. And the way you do that is that the expectation value, for example, of any quantity is going to be an inner product of the state applied on the operator. So this is abstract, but we can do a computation here for Sy. So what you do is you take your state, you transconjugate it, so you take its complex conjugate and transpose. You multiply it by the operators that you want to know the average of, Sy. This is this one. And you take the product with the state. And this is just a simple matrix computation. And you can see that it's going to give you h bar over 2 if you make the computation. And so the prediction of quantum mechanics is that in this state of the system, you will have, on average, the components of the spin along y to be h bar over 2. And you can do this similar computation for any of the other projections. So along x and z is going to be 0. You can compute the variance this way by taking squares. So you can extract these predictions. Okay. So these are the predictions of the quantum model. And you can see that at first sight, it's not very different from what I had in a classical stochastic model. Like it seems you can extract the same information. You can extract the prediction for what you will see if you run the experiments many, many times. But the question is it really the same? Is it really the same thing? Is it just that actually, well, this quantum model is just a very, very complicated way of writing a classical stochastic model. And for any state that I choose here, I can actually have a mapping to a stochastic model with a probability distribution where things are simple and understandable. And it took a long time to clarify that, and a lot of work, and the answer is no. And the answer was given by Yentao last week, and by Bell a bit before. And we can phrase it the following way. Do we have a genuine quantum effect? Is there something predicted by the quantum formalism that is not predicted by classical formalism? And the way to see that is to ask the following question. Is there a certain state psi, a certain quantum state psi, a certain combination of our degrees of freedoms represented by operator, such that the prediction of quantum mechanics cannot be matched by any prediction using a probability distribution for the spins? So this will be a quantum prediction, and this will be the prediction of a classical model. So can we find such a state and such a quantity that we can measure observably, such that the quantum prediction cannot be matched by a classical prediction? In which case, this will be a genuine quantum effect. And the answer is yes, and it was shown by Bell in 1964. So if you just take one spin, it doesn't work. But if you take two spins, and you look at their correlation, meaning that you take two spins, you place them in a certain state, and you measure their correlation in their direction, you can find such a quantity P. Again, Yentao showed how you did it last time. And this quantity P is such that if you have a classical probability distribution for the direction of the spin, it's always less than 2. But for a quantum model with this bizarre formalism, you can achieve a value of 2 square root over 2. And this value of 2 square root over 2 was measured experimentally, in particular by the Aspe team in 1982. And what it means is that, first, the spins obey the quantum prediction, so the quantum model of the spin is correct. But not only, you cannot find a classical model that would be equally valid, that would explain this prediction. Hence, this gives you a method generally to prove that a system needs to be described by a quantum model. If you can find such an observable for any system that cannot be accounted for by a classical model, then you show that the system needs to be defined. Okay? So that's like okay, I still have a bit of time. That's the very down-to-earth take. Now the question is, what does it mean in terms of interpretation of quantum mechanics? There's a bit of a leap there, but what does it have to do with the bizarre thing that I talked about at the beginning, like Schrodinger's cat? So let's put it this way. In fact, if the spin has a direction, like if you look at this writing of the quantum model, at no point have I said that the spin has a certain direction. I'm just telling you on average what you're going to measure and what you can measure, what are the possible outcomes. There's no underlying theory of what is the value of the spin until you measure. And actually, if you could attribute a value to the direction of the spin prior to its measurement, you could make a classical stochastic model, up to some caveats, okay? But precisely, if you could do that, if the spin had a value, you can build a classical model. And if you can build a classical model, then this quantity has to be less than 2. But we showed that's not the case because we find that there's a value larger than 2. Hence, you cannot build a classical model for the system, and the spins do not have a value until you measure it. And that goes against our classical intuition, okay? But that's not in the math, that's in the interpretation of the math, okay? And that's where it comes from, that the Schrodinger cat, for example, is not dead or alive until you open the box and you look at it. Until you measure it, you don't know. And my final point here is that, okay, there is this interpretation, but again, at the end of the day, when you construct this Bell inequality, when you make your experiments, the only thing that you see is the spins being in one direction or another. You never see anything bizarre when you do your experiment, okay? You just see spins taking some orientation. And after that, you take your table of measurements, you compute some correlation, and you realize that something quantum has happened. But you never see anything bizarre, okay? That's why there's this dichotomy between general impression on quantum mechanics and what you do at the end of the day when you're in the lab or on the paper. Okay, thank you for your attention, and just ask me a lot of questions.
Thank you very much, Amaury, for this very clear presentation on this very elusive subject. Okay, now I invite questions, comment, or discussions. Okay, go ahead.
Any genuine quantum effect other than the Bell's inequality?
Well, okay, so that's subjective. that's why it's not subjective. But in a sense, like if by genuine quantum effect you take my personal definition, which again is up to debate, is this thing that I can make a prediction in a quantum model that I cannot match in a certain large class of model. There are other types of Bell inequalities things. There is also Bell equalities kind of thing. Like you can predict. You can I say that? For example, you have other types of inequality that can be built in time. You do not two measures at the same moment of two systems, but you do several measurements in time that would be Legge-Gark inequalities. And now also you can make a prediction on the quantum model that you cannot make on the classical model. You can have Bell inequalities for multiple spins, more than 2, 3, 4. You can have also inequalities with, you can also things where you have only one system, which is a spin 1. And that's the Cohen-Specker theorem, where you can show that the prediction it's not so much in an inequality, but it's more that it's a bit different. Okay, it's a bit different. So let's stick it to Legge-Gark, Bell temporal inequality, and this kind of. So there are variations around Bell inequalities, and that would be this in the same class of genuine quantum effect. I can say more, but we can talk also about entanglement, but I think that's a bit different. I can tell you what.
Quantum computing is a genuine quantum effect.
I want to ask your personal view on whether there still remain some problems in quantum effect or everything is solved.
It depends on what you mean. I mean,
you mentioned a few questions. So my question is, in quantum mechanics, there's no unknown, unsolved questions?
Well, okay, so let's say like, so first, this is quantum mechanics. I suppose after if you go to QFT, maybe you can ask some other problems, like more fundamental problems on how you build a rigorous QFT. If you could have a lot to say about this, for instance. But then if you talk about interpretation, people are still fighting on how you can try to interpret this. There are also still people trying to fight on what is really the meaning of Bell inequality. You can read papers by Tim Modlin, for example, arguing that other people just don't understand anything about what Bell has done. The paper is literally called What Bell Has Done. And then there's a comment on what Bell has done by Werner, explaining that it's not correct. So there are still debate on the interpretation, and there are different ways of saying it. But let's say at the level of computation, it's not controversial. At the level of computation, quantum mechanics is controversial. That's what I would say.
So suppose you have a macroscopic spin. I mean, eventually, of course, to the classical limit. So somehow there should be some number of spins which makes an interpolation between 2 root 2 and 2, I think.
So can you say that again? So you're saying like if I have
talking about only one single spin, h bar over 2. Yeah. Suppose you have a lot of the spins aligned to the same direction, and then it eventually becomes a macroscopic, like a magnet.
Yeah.
That is classical. So how do you interpolate between the macroscopic spin and then the single spin? Of course, you can take h bar to 0, but here, if you take h bar 0, then everything is 0. So somehow you have to have another parameter which make an interpolation between the two. So what is it?
So my view would be that, like taking the standard of difference, which means to say like this thing is so what matters is the correlation between the two spins. So let's say instead of 2 spins, you have 2 assemblies of n spins, n being very large. Typically, you would want to preserve the bipartite correlation between this assembly of n spin and this assembly of n spins. But as n grows large, the disturbance, it's more prone to disturbance. So typically, as this thing gets apart, there's going to be some environmental noise. There's going to be internal correlation as well. So you want n spins to be correlated with these n spins. But at the same time, this n spin, they can interact in between themselves. And they can somehow scramble the bipartite correlation, I suppose. And all this disturbance doesn't have to do something with h bar. It's more that you have a large number of degrees of freedom. They are more prone to interaction with the rest, and this correlation is going to be washed away faster as n grows. So So it's not like a breakdown. It's more like it gets harder as n increases to keep the correlation stable, to be able to do this. But in principle, it's nice. You could have n extremely large, and if you manage to make a Bell inequality into it, you have a quantum system with n spins.
I just wanted to see it explicitly.
Yeah, I don't know how to write this.
So the classical limit is typically, in this case, of large s. So if it's spin 1/2,
Right.
if it's like spin 100,
Yeah.
quantum effect is a lot.
Oh.
So typically it's an expansion of 1/s, where it's a
So
spin s.
just the magnitude of S.
Just one particle with like an s spin.
How would you see that in the Bell inequality?
So you can basically do the computation, and I'm pretty sure the relative difference will scale with 1/s if it's a spin s particle.
Okay, so even for single particle, large spin is
Yeah,
enough.
exactly.
The computations that basically natural heritage.
Okay, so you're saying that it's the bound, right? That's why we discussed that there's S here or something.
Yeah.
But then does it? Yeah, okay. But the ratio in between the two computations does not.
So
It's the difference in between. It's like the space in between the classical result and the quantum result is getting smaller.
the relative.
Relative.
If you take n to infinity, then it
Yeah, but the ratio stays the same actually, so it's not so clear. Right?
The ratio doesn't stay the same.
This stays too.
Yeah.
Ah,
No, the other one won't be 2, right?
This
because
one
if
was
it's
spin
spin
and
s.
this one was.
For spin s, it's different.
it's not going to be 2.
It's not 2 anymore.
Okay.
Yeah.
Okay, so in that both.
I think the two examples that you guys gave are actually related, because if you take n spins 1/2, then you are doing basically representation theory of SU2 to the n. While if you take one spin with large n, you're like doing SUN. And for large enough n, one is a subgroup of the other. So mathematically, they're like the same.
Yeah. But they're not. Yeah.
Yeah,
1/6.
exactly. So that would be the only difference. But like,
That's a huge.
And you can have internal correlation.
yeah. No, but I mean that both are like large n limits of some different groups.
The difference between the two scenarios is very large.
Yeah. But the mechanism for going classical mathematically is the same. You just take like some group with the large n, whether it's SU2 to the n or it's SUN. That's what I wanted to say. I'm not saying it's the same.
It's reproducible. That's right.
Okay, anything else? Oh, go ahead.
One naive question is, when you have the electron-positron pair production, if you measure electron here, you know positron here.
Yes.
Right? Do you say this is entangled or not?
I think actually, if you produce electron-positron from the vacuum, they are entangled. They are in entangled state. Typically, if you produce particles from the vacuum, they will be in an entangled state.
You say entangled.
Yeah, they are. Yeah, they are entangled.
That you say, even that this is, people say this may be just a conservation law, classical conservation law. So nothing to do with, the quantum mechanics.
It has to do with quantum mechanics if they are produced out of the vacuum, right? Because the fact that you can produce things spontaneously from the vacuum is a property of the quantum vacuum. But if so in this sense, I would say that if you produce them out of the vacuum, they will be entangled, and that's actually, you can write it, and you can also violate the Bell inequality with the position of.
So you say that this is entangled. Same thing that say B boson, anti-B boson.
Yeah.
You say they are entangled.
I would say so. If you take a mathematical definition of what is entanglement in the sense of the product, you cannot write the wave function as a product of wave function for. Then I say yes. And actually you can violate the Bell inequality with this thing.
Yeah. The reason why I ask this question is that consider spin 1/2 particles, two of them.
Yeah.
And if they are moving extremely energetically from each other,
Yes.
then spin 1/2 particles tend to be the Hertzian reactive. Then Hertz means, if you start, say, decay from the spin 0 particle and very energetic electron-positron pair, but they are in, say, Hertz state. then either +1 or -1. Then, this may be the classical correlation or quantum correlation. But you say electron-positron pair is already quantum, then it's okay. But people often say that electron-positron thing that that's a classical conservation law. Then, when the spin one-half particle is moving very slowly, then your argument like Bell's inequality and so on, that's valid. But if they move extremely energetically each other, then they may become the eigenstate of the helicity. Then helicity the +1 -1. Then people may say this may be that's a classical. Then entanglement to the energy dependent. But you do not agree with this argument.
I would say that okay, so I'm not sure I understand it fully because maybe I don't have the background to understand it, but let's say you're saying that some of the entanglement in the helicity degrees of freedom goes away if the energy is too low. If this thing is produced out of the vacuum and they're considered as an isolated system, I would say they're entangled anyway. So if their helicity state is not entangled, the entanglement has to go away, has to go somewhere else.
In the usual case of the Wigner's definition, using Wigner's definition, then the spin state was defined as a rest frame. So even if two are very, very rapidly, moving away each other, if you go to rest frame of this one and rest frame of this one, then they are just classical behavior. Classical means classical quantum mechanical behavior.
Non-relativistic.
Yeah, but if they are moving very fast and if we measure them in the laboratory frame, they may be helicity oriented. Then no more entanglement in a sense, because if this helicity, this one is the other way, because started with the spin velocity.
Yes, so I see what you mean. You're saying that this would be just a classical conservation.
Yeah.
This is but I think sometimes the classical conservation when you go to the quantum formalism would translate in entanglement precisely. So for example, if you think of production of particles at the vacuum and you write down using a quadratic Hamiltonian that conserves momentum, this is the conservation of momentum that imposes that when you create a particle with a certain momentum out of the vacuum, you have to create another one.
Yeah.
Nonetheless, if you look at the wave function of these two particles that you've created, that somehow have to be created in pairs due to momentum conservation, they will be entangled.
Oh, I see.
So somehow there's a traduction of the energy, the momentum conservation at the level of the Hamiltonian that translates in entanglement of the pairs.
In my view, everything clear. But some people say, for the electron-positron case, they are just, classical one, nothing to the quantum mechanics. Because if you have the positron, the electron here, right? And that's the classical conservation law. But you say they are quantum correlated.
Suppose you have a boson like pi plus pi minus pair created and then far apart, and then it's a boson, therefore you have to have a symmetric wave function. Therefore, you have to still superposition of the in this state, it's not just a product state, but it's a superposition.
Yeah, well, without knowing quantum mechanics, if you make the pair creation, if you make the electron, you definitely know the positron here. That's nothing to do with the quantum mechanics.
Yeah. So actually, some people would. So there's a very nice article that I can find where people try to explain in this kind of term, like because in this entanglement picture, sometimes people say, oh, but this is trivial because you're just telling me that if I measure up somewhere, I'm going to measure up somewhere else. But if I start with up and up, then it's obvious. It's just, but actually there's a paper that tried to explain with twins doing telepathy, what is specific with a Bell inequality violation. How having a Bell inequality violation is a type of correlation that allows you to do things that are not just telling that because I measure up, the other guy's gonna.
Yeah, but in the case of the spin one-half particle, you have, in a sense, infinite number of freedom.
Absolutely, exactly.
Yeah,
You have to measure also not
in
what
that case, entanglement argument is okay. I agree. But when the electron positron pair or B anti-B protection, I am not quite sure. So I would just ask.
Another thing is that if there's conservation law on the in the system, then you don't have tensor product structure anymore. So the Hilbert space is no longer tensor product, does not have tensor. It's constrained by the conservation law, and that ruins a lot of definition of entanglements. So I mean that's why spin is used instead particle number. So it's important that you don't have conservation law to keep the tensor product structure of the Hilbert space. So
Well, but my point is that without knowing quantum mechanics, we can discuss the electron positron pair protection. And we always sure, okay, if you mean electron
yeah.
positron here.
Yeah, typically that's not regarded as a quantum effect.
Okay, thank you very much.
Okay, thank you very much for very lively discussions. Is there any further question or discussion? Okay, if not, let's thank Maury again for his very interesting discussion and the topic. Okay. All right, so people at the common room can go ahead and continue discussing. Thank you very much for coming.
If you don't have